Okay, yeah, comfortable here. All right, so there's a topic in 3.5 when we talk about kinetic molecular theory and gases, where there's this topic called the Maxwell Boltzmann distribution curve. So I'm going to go through what that's all about. Okay, and let me just, oh man, take me one extra second here. Click, 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 click. There we go. So we're going to look at Maxwell Boltzmann distribution curves. So these are curves that discuss gases. There's it's named after two different scientists, one with the last name of Maxwell, and the other one is Ludwig Boltzmann. They did not work together. They were working kind of simultaneously at the same time, but not really together. And they both came up with the whole these distribution curves. They were curious about gas particles and their movement and their speed. All right. So let's look at a couple things. Let's discuss first when we measure the temperature, right? So I have a container here, and we'll put 1, 2, 3, 4, 5 molecules of gas in there. And I'm going to put a thermometer into here. Okay. And I'm going to record the temperature. All right. And I see that that temperature here is, let's say that it's 400 kelvins. Right, well, what does that mean? What does that mean? Well, you need to know that temperature is directly proportional to the average kinetic energy. All right. And then the average kinetic energy, or the kinetic energy, is equivalent to 1/2 mv squared. So at a given temperature, the average kinetic energy of a substance is the same. So two different gases at the same temperature have the same average kinetic energy. There's two different gases, 5 different gases at the same temperature have the same average kinetic energy. All right. What we will see, though, according to this second equation here, right, is that if, I didn't want it to make a perfect square, but all right. Notice, and I elaborated on this the other day, if the mass, and you would think molar mass, goes down, right? All right, molar. This for us guys will be molar mass of the particle, okay? So if the molar mass goes down, then the velocity must go up in order for the kinetic energy to remain the same at a given temp, right? So what I'm saying is, if I have a light gas particle in terms of mass, will have a higher velocity. Remember, velocity is a speed. If you didn't know that, velocity is speed. Velocity is just speed with a direction. They're essentially the same, just add a direction. And here we have the kinetic energy is the same because we're at a given temp. And we would have a higher molar mass. So if our molar mass was larger, we would have a smaller velocity. And that would allow that kinetic energy, once again, to remain the same. So what I'm saying in the second part here, right, is the higher the molar mass, the lower the velocity. And this is what I had, hold on, the lower the velocity. And once again, that allows for, at a given temperature, the kinetic energy of any type of gas to be the same. But what will change is the velocity. The higher the velocity, the lower the molar mass. The lower the velocity, the higher the molar mass. So this is when in class I had said, think about football players, the big old football players, big molar mass, they don't have that much of a speed. But when they hit you, it's like being hit by a little guy running real fast. They're going to hit you with that same, and we're calling it that same temperature. Okay. Same kinetic energy. All right. So we've got that there. Now let's look at two gas containers. All right. And they'll, be the same size. And we'll have particles of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And those will be our molecules of, say, nitrogen gas. And here we're going to have the same number, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have the same amount of gas, same volume. Let's say that this is at a temperature of 300 kelvins, and this is at a temperature of 400 kelvins, okay? Well, I also want to point out the temperature is proportional to the average kinetic energy of all the gas particles. So what does that mean? That means in a sample of gas, and let's look at our 300 degree temperature, we'll call this gas A, okay? We have one gas particle moving with a little bit of kinetic energy. Maybe we have another one with a lot of kinetic energy, all right? We have another one with a little bit, another one with a little bit, maybe another one with a little bit more. But on average, they're pretty low, okay? And these are obviously, right? They're different, and some are fast and some are slow, okay? Well, if we look at our other gas, same number of particles, higher temperature, well, a greater number of these particles are going to be moving at a higher speed. Why? Because the temperature is higher, but there will still be some that are moving at slow speeds, maybe some barely even moving at all. Okay, but a larger number of them will have a high speed than the lower speeds. Okay, notice though, for gas A, it might have the fastest moving particle of them all, but on average, it's a lower speed. Okay, all right. So what the Maxwell Boltzmann distribution curve is it explains what's happening here in a curve. So let's draw what one might look like here. Here's our, down here we will have our speed. This will be in meters per second. Over here we will have our number of particles. All right, we'll have our number of particles. Well, let's look at gas A first. Gas A is moving slower. So I'm going to kind of, that's a little too high. I'm going to try to reach for this right here. I don't know, but whatever. So I'm going to kind of go like this. Right? Whatever. So there's kind of the top middle of my curve. I'm not very good at freehanding this stuff. Okay, this is gas A. And then for gas B, let's get a different color. And gas B is going faster. Gas B is at a higher temperature. So you know what I'm going to do? I'm going to flatten that curve and push it over. So I'm going to kind of go like this. Okay? Now, this is gas B. Now, this is not to scale, obviously. All right? Now, a couple things you need to know in looking at this curve is that the area under the curve is equal to, or is in relation to, I'm not going to use that sign. The area under the curve is the number of particles. Same number of particles, same area, okay? And I say that for one, because in order for it to be the same number of particles, if we flatten it over, then we need to spread it out, right? So when we went, gas A, which was at a lower temp, was higher. Gas B at a higher temp, and I'll explain why in a minute, was flattened, and we had to spread it out to keep the area under the curve the same. Because we do, in fact, have the same number of particles. Remember, we had 10 particles. Obviously, there would be a lot more in both samples, 10 moles, 10 particles, however you want to look at it, okay? Now, notice when you look at the curve that this gas is moving at this speed, whatever, that's and this gas, the majority of the particles are moving at this speed, right? The top of the line would represent the majority of the particles. So what I see for gas B is that more particles, right, are moving at a higher speed. And what I notice for A is that more particles are moving at a slower speed. All right. Now, once again, this is the same type of gas. The only thing different is the temperature. The amount of the gas is the same, and the type of the gas is the same, okay? If I was to have another sample of this gas, and it was at an even higher temperature, then I would have to flatten this curve and spread it out even more, right? So this would be my highest temperature curve. All right, so if, let's say they look like this, maybe like this, and like this is going to be the lowest temp, and this is going to be the highest temp. So if you're not seeing it visually, as the temperature goes up, the curve flattens and scoots to the right. So the top of the curve is lower, and it's further to the right, because down here is the speed. So we have more particles at a higher speed, the higher that temperature goes, okay? And remember, this is your number of particles, which is referenced by the area under the graph, under the curve. Okay, that's about it, to be honest with you. I wrote some notes up here earlier to make sure I covered everything. Maxwell Boltzmann, same gas, different temps, that what we just did. Let's look at a different gas at the same temp, all right? Excuse me, I need a tissue. So let's say that we have speed, same temp, different gas. All right, so I'm just going to draw two curves. And let's see if we could infer which one of these gases has a higher molar mass. Okay, same temp, different gas. So let's see, same temp equals same kinetic energy. all right? Kinetic energy equals 1/2 mv squared. So the heavier gas, heavier, right? This is a constant because we have the same temperature. The heavier gas must be moving slower. Therefore, let's look at this again. This is my low speed. This is my high speed, right? So this low speed must be my higher molar mass, and the high speed must be my lower molar mass. So you could also think about it like that. All right. It is also interesting to know that up here, when we talked about nitrogen, I think this is our pretend nitrogen curves at different temperatures. Do you know that at 300 degrees Celsius, no, kelvins, at 300 kelvins, which is a little bit warmer than room temperature, the average speed of a nitrogen molecule is 422 meters per second, which is equivalent to about 944 miles per hour. And there are tons of nitrogen particles all around you, and they are colliding with you at this speed or this speed, but they're so small, it doesn't hurt, right? It's just the normal pressure around us, but that's what causes our air pressure, okay? Now, I wrote something up there. I wrote diffusion and effusion. This is quite simple. I may have too many F's or S's. I don't know. That is not my concern, guys. These are both the movement of gas. Diffuse is the movement through a membrane, such as, I'll explain that in a minute. And effuse is the movement through air. Actually, I got that wrong. Diffusion, effusion. No, I didn't. I think I got it right. I may have that wrong. All of a sudden, I'm a little. I don't even know if I have that right now. So we can fix it if we need to. You won't be asked it, but I know it, but all of a sudden I'm a little confused of it. One of them is gas. I always explain it with a stinky trash can. Gas. Okay, maybe I'm right. The gas particles, you got a trash can, open trash can, right? There's your trash, and it stinks. Well, when your trash can is open, the gas particles just go like this, and they fill up your room, and the kitchen starts to stink, right? So what do? You close the trash bag, right? And now the gas particles are kind of stuck on the inside. Of course, they will escape out, but not all of them. So one of these is effusion, one of these is diffusion. I utterly should know the difference, but I don't feel like stopping and looking it up right now. So I'm going to assume I'm right. If I'm wrong, I'm sorry, I'll fix it. But that's all that is. Now, so the rate at which that occurs of either, it doesn't matter. And I think there's two F's there, diffusion, or the rate of effusion is indirectly proportional to molar mass, right? Which is exactly what we just said. As the molar mass goes up, the rate of these gas particles' motion goes down. All right, so the speed or the rate at which in which is a speed, sort of, distance per time, is going to go down, the heavier a gas particle is. So if I'm standing right here in a room, right, and you're over here and you spray a gas, right? So this is a gas. This is quite a drawing, huh? And here's me. Here's Miss Murphy over here. And when that gas is sprayed out, right? Let's say that we get blue heavy guys. And say it's a mixture of gases. I need it to be. And then we've got the light guys. And what we see is the lighter, and I'm about finished here, guys. These lighter gas particles have traveled further than have the heavier particles. So if there was a smell to this gas, I would smell the lighter gas first because it would reach me first because its rate is higher. Its rate of travel, you could think. Okay. Sorry. I think that's good. So I'm gonna leave that there, and I'll post this to the classroom, guys. Stop and end.